today's discussion is on Huffman coding scheme. It is again variable length coding scheme, encoding scheme. So again, you have the similar set of inputs even in this case, like the ones we have studied already, and we were trying to find out some improvement compared to the previous coding schemes. Earlier, we have studied Shannon coding or Shannon-Fano encoding, some tree-based schemes, etc. So similarly, this is another one, but it is not yet another one. It has some improvements compared to the previous ones. By the end of this lecture, you should be in a position to understand what's the improvement in this case. I mean, benefit of using Huffman coding compared to the other schemes, or you should be able to justify whether it has any improvement or not. I mean, you will be able to compare by the end of this lecture. So altogether, I have 15 slides for today, and initially, for the first 5 slides, we will see the motivation for today's talk, and also this will revise some of the points from the previous lectures, such as Shannon's or Shannon-Fano encoding, or the one we studied in the very previous lecture. Okay, so Huffman coding, as I said, it's another variable length coding. So it is proposed by David Huffman, who was a graduate of MIT, United States. And he introduced his findings in one of the literatures here. If it is possible, you go find out this literature in the internet, it's available for more details of this. But anyway, for understanding the Huffman's coding, how the Huffman coding works, today's lecture will be sufficient. But if you need more mathematical proof regarding some of the key findings there, of course, you can go back to this literature and find all the details there. But it is beyond the scope of our university syllabus. Okay, so what is the application of this? So applicable for data transfer. For example, if you have any text files, some sources, maybe teletypewriter or a fax machine, which generates different symbols when you want to, like when you want to transmit any text files. And similarly, it is applicable to other kind of data also. And then another one is ASCII, when we represent the text files in ASCII code, right? So each character occupies 8 bits. So can we do some improvement on that instead of ASCII? Because ASCII means any character you need to represent by 8 bits. But if we use some coding schemes like the Shannon-Fano coding or Huffman coding, is there any improvement possible? That we will see today. Okay, now, so minimum number of bits needed. For example, if you want to transfer or transmit any or store any text message emitted by any source, then if you use ASCII coding, then every bit occupies 8 bits. But if you use some other coding schemes, maybe as Huffman coding as example, then you should be able to represent every bit by variable number of bits. I mean, every character by variable number of bits. But our objective is to represent every character by minimum number of bits. That's the objective of any of the coding schemes, because we are targeting mainly cost saving in terms of resources, maybe money or storage space or bandwidth and so on. Then Huffman coding is a form of statistical coding. What's the meaning here? So meaning of this sentence is, it observes the probability of the symbols and then does the coding. That is similar to the earlier coding schemes also. Even earlier coding schemes, what we studied, they are also the statistical coding schemes, because they also consider the probability, and based on the probability, we assign different codes to them, right? Again, one more background information. Not all characters occur with the same frequency. So if you see any English, if you consider English language, then different letters will occur with a different probability. For example, A may occur more number of times, or any vowel, if you consider it, occurs more frequently than characters like, for example, here. Some characters like E or S They are very frequent in a sentence or in a word, but Z or X, they are not very frequent, right? So, but if by using the existing way of representation, that is, or a well-known way of representation, I should say, ASCII character coding, then it requires 8 bits or 1 byte for any character. E is represented with 8 bits, S is represented with 8 bits, or if it is, even if it is Z, it is represented with same 8 bits. But it is not necessary to represent every character with the same number of bits. If we can do it in a better way, or a better coding scheme should consider the probability of occurrence. That is what the idea of statistical coding. Any saving in tailoring the codes to frequency of character? Is there any benefit by doing that? Any saving possible? A good code word lengths are no longer fixed like ASCII. So in ASCII, there is no tailoring. Any character we represent by the same number of bits. But it says code word lengths are no longer fixed. Okay, and then code word lengths vary and will be shorter for more frequently used characters. So again, if you have studied the previous lectures, we have found this. This is one of the characteristics of a coding scheme, an intelligent coding scheme. So we have assigned the number of bits lesser for a more frequently occurring character. And we have assigned large number of bits for a symbol or a character that appears less frequently, right? Okay, now regarding the Huffman coding, let us consider an example. This is also the intuition for previous coding schemes. So now you consider a sentence here or a statement here. Oh man, what a scene! So this is an exemplary statement or a sentence. So in this one, we will count the occurrence of all the characters in the text. For example, O, how many O's we have? O occurs 1 time, right? H, how many H we have? 2 times, right? And M, there is 1 M. Similarly, A, how many A's? That is just count here, maybe 2 times, okay? And all these characters from this statement I have listed here. How many times each letter occurs here? And also space occurs 4 times, right? 4 times, 1, 2, here there is a space, and here one more space altogether, 4. So if we use the ASCII coding scheme, then each letter will be represented by 8 bits. But there is no need to represent every character by 8 bits if we use some intelligent scheme. That's why we were thinking about how to tailor the number of bits in a code word by considering the probability. In previous coding schemes, we have done that. And we have concluded that the characters that appear more frequently should be represented by shorter code word, and the characters that are not so frequent can be represented with longer code words. Okay. So next, we have also seen representing the binary tree, right? The character and frequency. I mean, for every character, how frequently they occur. Based on that, we have represented the binary tree. That's in the very previous lecture. Similarly, in today's lecture, we will be doing that indirectly. But at the end of the lecture, I will ask you a question. Did we use the binary tree today or not? Please watch it carefully. Okay, then in that case, I mean, even in today's case, we will be doing placing the nodes in a priority queue. We will assign different priority to different messages based on their probability of occurrence. And the lower the occurrence, higher the priority in the queue. Okay, so okay, right now that was the intuition for today's lecture, and also that was a general discussion regarding some of the features that we studied in the previous lectures. Now, coming back to the main topic of today's discussion, that is Huffman encoding algorithm. So here, so before moving further, I just want to confirm that whether my voice is audible and the screen is visible. Please, class representative.
Yes, sir.
Yes, sir.
Thank you very much. So I'll continue. So Huffman encoding algorithm. So this algorithm has different steps. First, we will see what are the different steps. And then, as usual, we will have an example, one or two examples, where we will be exactly using these steps. So the first step is, in this algorithm, we have different symbols emitted by a source, and these symbols will have different probabilities. That is the input given. So we need to perform Huffman encoding on that particular input. That means we have a list of symbols, A, B, C, D, and so on. And they occur with different probabilities, 0.2, 0.3, 0.1, 0.05, and so on. So first step, what is the first step if that is the input? The first step, the source symbols are listed in the order of decreasing probability. So I have highlighted some of the terms here in the different color. Okay, so when we have the list of probabilities of different symbols, first step is to arrange them in the decreasing probability, highest probability first, lowest probability last. Next, two source symbols of lowest probability are assigned 0 and 1. What's the meaning here? I will use the pen to write something here. For example, the given probabilities may be 0.5, first one, and the next one 0.3, and the next one is 0.2. So this is the first step, right? I have arranged the probabilities in the decreasing order. In the second step, says two source symbols of the lowest probability. What are the lowest probability? This and this, right? So they are assigned 0 and 1. Just we will assign a code here 0, and we will assign a code here 1. Okay, then we will move on to the next step. That is the third step. Please watch the third step. Combine, that means add these two symbols of lowest probability and generate a new probability or a new symbol. What's the meaning here? So right now I'm in the going to the third step. So what I should do, the two lowest probabilities 0.3 and 0.2, I will combine them. That means add them. What's the value in add? 0.5, right? Okay, please remember that it is 0.5. Okay, so I'm adding here, that is 0.5. That is the new probability, or as a new symbol, 0.5. Next, fourth step, the probability of new symbol is placed in the list, decreasing order, as in step 1. What's the meaning here? So it means the new symbol, what I have generated here, 0.5, I should arrange it along with the other symbols or other symbols of probabilities in the same decreasing order. So right now, the new symbol generated is 0.5, right? 0.5. I'm writing here 0.5. Okay. What is the other symbol left? That is this one, right? This is left. So this is 0.5. Also, this one is 0.5. Now we need to arrange it in the decreasing order of probability. Just sort it like you have done in the first step here. So 0.5, this is also 0.5. You can sort it in any way, right? Because sorting means it's the same number. I mean, same values. So you can sort it in any way. But what we do is we will place this 0.5 first here. I mean, we are progressing to the next step. The 0.5 is here. I'm placing that 0.5 here. That is 0.5. I have placed this 0.5 here, and there is one more 0.5, right? That is left initially. I'm placing that one here. Again, it is a sorted order. Since the values are same, they are same. So what is this? This is here. Okay, so this is the fourth step. So after the fourth step, what you can see here is, again, we have some probabilities. They are in the sorted order, just what you have done in the first step. Okay, then step 5, repeat until you are left with finally only two symbols or characters. That means, what's the meaning here? Repeat step 2 and 4. So in the step 2, what we did here, we assigned 0 here and 1 here, right? So that's what we have done. Okay, now I will open my pointer. Okay, so this is what the Huffman coding is. So you should repeat this. How long? Until you are left with only 2 items here. Okay, so this is the initial list. It's a sorted list. In the first step, in the second step, what we did, we considered 2 lowest probabilities and then assigned one of them as a 0, another one as 1. Okay, and then we got a new value, that is 0.5. Now we have to consider this one, 0.5, along with the other symbols in the list. There may be many symbols in the list, but in this example, there is only one symbol here. So all these symbols except these two and the new symbol here, we have to sort it. That's the next step here. So the remaining symbol in this list was 0.5. The new symbol generated is 0.5. Just you need to sort them. 0.5 sorting is 0.5 itself. I mean, they are 0.5 and 0.5. But this value is placed first, and this value is placed here. Of course, you may ask a question, why can't we place this one here and this one here? We may do that. But at the end of this lecture, I think the very last slide of today's lecture will justify the reason for this. Of course, you can do this in any way. Just it should be in the sorted order. For example, if this value was 0.6, this will appear 0.6 here, and this will appear here. That's a sorted order. Since they are same, now we will take the privilege of putting this new item first and the old item here. Okay, and then continue the same steps. Like we have 2 elements here, we will combine those 2 last or the lowest probability ones. Here only 2 items, so we have these 2 are the lowest probability ones, and assign a 0 here, 1 here, and yes, you are done, because it says only you are left with the 2 elements. Then you have to stop. Repeat until you are left with only 2 items in the final list. So I have highlighted some of the key terms here so that you can easily look at those terms and understand. Okay, now we need to, that's a final step. What is that? Trace the sequence of zeros and ones assigned to the symbol in the backward direction. So now we have assigned some 0 here, 1 here, some 0 here, 1 here, right? Now we have to read it in the backward direction. Backward direction means from here to here. Okay, and for whichever symbol, what code, that is the code word of this method, Huffman coding method. For example, if you want to find out what is the code word for this symbol, you have to read from this side. From this side, you have to come back to here. In case you want to find out what is the code word for this symbol, you have to come back from here. What is the path to come back here? Like this, and like this, right? Okay. Okay, that's the method. These are the different steps. And now I'll go to the next slide where we have a formal example. Okay, you see here, now I have given a rough idea about the Huffman coding, and now you will solve this example. Maybe you can try by yourself, but maybe you can see this example right now. And I have one more example that you may try by yourself if you have a paper and pen. Okay, right now you concentrate on this slide. We have 5 symbols, the question, and their probabilities are 0.4, 0.2, 0.2, 0.1, and 0.1. I use a Huffman encoding scheme. So I will use a table here because when I write some arrow marks, it looks neater if I use the table. It is easy to use a backward path. So 5 symbols are here, 1 to 5, and now the first step is to arrange these symbols according to their probability of occurrence in the decreasing order. If you see here, it's already in the decreasing order. So it's easier for us. Otherwise, we know how to sort in the decreasing order. So how it looks like 0.4 to 0.1. So basically this I have listed here. Okay, that is the first step. In the next step, what do? We consider the two lowest probabilities, right? Two lowest probabilities. And then what do? We assign a 0 to one of these and 1 to here. It can be reversed also, again, but we will use one method. Okay, right? I mean, a method, the same method throughout. So I will assign 0 here and 1 here. And then what's the next step? You have to just compare these items and the new item generated. 0.1, 0.1, how much? 0.2, right? Addition. So a new item generated is 0.2, and there are 3 items in this list. You just need to sort them. If it is already sorted, oh, no problem. Okay, now we have a 0.2 here. Where should we place that? The first item here will be 0.4. The next items are 0.2, 0.2, and 0.2. So this 0.2 here generated will go to the first position in the sorted list here, right? Something like this. And then this 0.2 is where? Just here. This 0.2 is here, just here. Okay, all are same 0.2s, but we are just moving this item first. That's all. And again, this is a sorted list. So I think now this step is clear. So this item, new item is 0.2. It can be anywhere, but we have moved it to the first place in the sorted list. And this item, then it is here. This item is here. So, okay, now we will continue the same steps. That is step 4. Step 4 is to just repeat. Step 5 is to just repeat step 2 to 4 again and again until you are left with only 2 elements. So, okay, now continue. So the lowest 2 elements here, lowest priority elements are here. Now we want to combine them. While combining them, we will assign a 0 here and a 1 here. Okay, the new element generated has a value of 0.4 because 0.2 plus 0.2. Yes. Now where that 0.4 should go to? It should go to the top, right? Because other 2 candidates here are 0.4 and 0.2. And this is a new candidate that is 0.4. So anyway, 0.4 is the first in the list. But this 0.4 will go to the foremost element here, as shown in this step. And this 0.4 will slide to this position, I mean second position. And this 0.2 will slide to this position. All right, here. And can we continue further? Of course, because we have 3 elements here. So we have to continue until we are left with only 2 elements. So continue the same step, repeat. So these 2 are the lowest priority elements. We have added them, resulting in 0.6. So let us assign a 0 here and 1 here. Now our new symbol's probability is 0.6. The existing symbol, only one symbol that is left is 0.4. So we know how to sort 0.4 and 0.6. Obviously, it will come to the top position. And 0.4 will slide to here. I mean, this is a sliding order, I mean, arranged order of decreasing probabilities. Are we done? Almost, right? Because we are left with only 2 elements. So we will assign 0 and 1 here. Then if you add, you are getting 1. That's the maximum probability possible. So we will stop at this stage because if there are 2 elements left, we will just assign the codes for them and we are done. Okay, so this is these are the steps that can be mapped to the step 1 to step 5 in the previous slide. And final step is to assign the code. We did all these steps to identify which symbol represents what, how to represent each symbol. So we have to do that now. Okay. Okay, I will just tell you how to do that for maybe one symbol. So first symbol is S1, right? What is the code word we can assign from this table? So we need to find a backward path from here to S1. How to go? Maybe like this, and like this, this, and to S1, right? This is the backward path. When you go in the backward direction, if you encounter any of these symbols like 0 or 1, that becomes the code word. I will use my pen to show you something. Maybe I will use yellow color. Yes. So now I want to assign what is the code word for S1. Okay. So the backward path from here is this. I should go here down, and then I go here, and then here, and here, right? This is S1. I will get S1 here. Now, along this path, did you see any zeros here? Yes, there is one zero here, right? I mean, this kind of zeros, which we have assigned, okay? And in the path, did you see one more zero here? Very nice. And do we have any more zero or one here? No, right? Yes, so, okay. So that gives us the code word for S1, that is a 0 and 0. That becomes a code word for S1. Is it right? I will go to the next slide where I have listed. Yes, 0, 0, first one is the code word for S1. Next for S2, I will use my pen again with a different color. Maybe I will use purple. Okay, now I want to find for S2, how to go to S2 from here. Maybe I will first find out the forward path because that is much easier for me. Maybe this is a path, right? Okay, yeah, this is a path. Okay, so this is just using a trick to find out the path. So actually, this is the reverse path, right? From here, you can go this way, and this way. This is the reverse path to S2. Okay, so now you have any ones and zeros along the path. Obviously, you will have that is 1 here, and then where did I go? Here. That means I came here. I started from here, and then I went through this path at this arrow, right? Then I went through this one, and this one, and this one, and this is 0 I found. And then, okay, there are no zeros after that. So my code word is 1 0. Right? Yeah, okay, right. My code word is 1 0. Okay. Similarly, you can find the code word for other things. For example, let us do SY. SY with some other color. Maybe I will use this light green. S5. Where is S5? I cannot locate my pen. Okay, here. S5. The path is here, right? I come here and I go here, and then I go here, and I go here, then I go here, and I go here, and I go here, right? So this is the reverse path. So I will get a 0 here, and then I will get okay, this arrow mark. I come down here, and I get a 1 here, and then I go here, where? Okay, here, and then I finally go to 1 here. So is it 0, 1, 1? Yes. So that is 0, 1, 1, S5. Okay, so this is how we need to do the backward tracking. Okay, I think you have understood these steps. So S1 is, please note this, I mean this step, I will use my pointer again. And yes, S1 is represented as 0, 0, S2 is 1, 0, S3, 1, 1, and S5, 0, 1, 1. So here, in this case, did you notice something? Or what is the conclusion here? So the probability which is highest is represented with the low number of bits. Probability which is lowest is represented by more number of bits. Okay, and one more question. Did we use any tree structure here? If someone answers this question, point maybe 1 mark bonus. Did we use a tree structure here? If we have used a tree structure,
Yes, sir.
where? If we have not used the tree structure, justify.
So we have used this tree structure, sir.
Where is the tree structure?
It's like you're asking a computer, like a programmer, saying that whether it is state one or state two, depending upon the probability. First, we are checking. So if it is state one, it will send you zero. The probability thingy. Then again, it will mean sorry. If whether it is state one, can you show me that the code word which we got?
Yes.
It will ask whether it is state one or state two.
Okay.
If it is yes, then it will send zero. Then it will ask whether it is state one. Then if it is so, then it may send you zero. So we will end up getting S1. If not, then it will be state two.
Okay.
For the another branch of the tree, when it had asked us whether it is state one or state two, that is one. That is nothing but the remaining state. Again, it will ask whether it is state three at the first.
Okay.
Then it goes on like that.
Okay. Okay. So may I know your name?
Sherwin.
Okay. So thank you very much for your answer, and you have a right answer. So you get a bonus point of 1. So my policy here is a student can get a maximum of 2 points bonus in 1 semester. So you have achieved 1 point right now, and you can try for 1 more in this semester. Okay. Of course, you can try, but you can collect altogether maximum of, any student can collect maximum of 2 points, 2 marks as bonus. Thank you very much and congratulations. I continue. Okay, now that is how we assign the code words based on the, maybe I want to add one more point here. So if you have seen this arrangement, first we arrange everything in the decreasing order, and then we targeted the elements or the symbols that have the lowest probability first, right? And then again, lowest probability first, and it continues. So why did we do that? Instead, we could have considered highest probability first and done that, right? So we have not done that because our intention is to represent the symbols with the lowest probability with a large sequence of code. The symbols with the highest probability, we want to represent by a limited number of bits. That's what happened, right? Highest probability is only 2 bits. The lowest probability is maximum number of bits, 3 bits. That's why we targeted first the lowest probability ones, and then we went on to the highest probability ones, because those highest probability ones in this tree will appear at the end. So just you will assign a 0 or 1 here. The lowest one will appear throughout. I mean, it is just a repetitive process, right? Recursion. So they will contribute to the information that we generate in every step. So they will have more number of bits in the process. Okay. Okay, now we will solve some other sub-questions regarding to this problem. So the next question is, since we have already found the code word, Huffman coding method, using Huffman coding method, find the average code word length. Then we find the entropy, and then we have a new term here, variance of average code word length. I will tell you why we have introduced this. But these two terms we have already seen, just we will use them again here. The first one is the average code word length. Generally, it is represented as L, L prime. Okay, so that is what L prime is the average code word length. Is nothing but the probability pi multiplied by Li. Li is the length of the code word. For example, for the first symbol S1, the probability is 0.4, and L1, how many bits? 2 bits. For the second symbol, 0.2 is the probability, and Li is 2 because there are 2 bits in its code word. Similarly, for other bits, for example, S5, the probability is 0.1, and the code words are 0, 1, 1, so it's 3 bits. Yeah. So altogether, just the multiplication and basic maths, and you get a value of 2.2 in this case. Next, entropy. How to find the entropy? You know, entropy is a summation of probabilities and log of 1 by probability. So the first symbol, probability 0.4 log of 1 by probability, and do the summation for all the symbols. For all these symbols, you have the probability. You can just compute the entropy here. Okay, average code word length is 2.2. Entropy is 2.12. So by seeing this, do you remember any of the equations or theoretical concepts that we studied earlier? The code word length, in case of a variable length coding, the average code word length L prime or L dash, whatever, and the entropy, they have a relation, a very generalized relation that I have discussed, I think in maybe a couple of lectures I have discussed that. If you remember, I mean, you can keep thinking. Okay, right now I have some note for you here. The entropy is lower than the average code word length. This we have seen. Do you remember this equation somewhere? H of S is always less than or at the most equal to the average code word length. That means when you consider the average code word length and entropy, always entropy will be the lowest, or it may be equal to the average code word length. And obviously then L prime, that is the average code word length, is less than entropy plus 1. Okay, the next point from the Huffman coding. So this is in general, also applicable to Huffman coding, applicable in general to any of the variable length coding schemes. Okay, now here, regarding specifically about the Huffman coding. So while in Huffman coding, we assigned a 0 and 1, right? The lowest probability symbols are assigned, one is assigned a 0, one is assigned 1, right? You remember that? Maybe I'll just go back to show you. Yeah, we assigned a 0 here, 1 here, right? That's what I'm referring here. Here in this step. So 0 and 1 can be assigned in the other way also. I mean, the upper one can be assigned 1, the lower one can be assigned 0. Even the combined symbol can be placed below. So when you add up two symbols, in the next step, you will please place it to the topmost element, right? As a topmost element, if the other symbol also having the same probability. For example, in the previous example, what we discussed, there are two items, 0.5 and 0.5, but we placed the new 0.5 at the topmost position, right? So that need not be the case. It can be placed below also. But what happens then? In that case, of course, the code words may differ. The S1, symbol 1, may have a different code word. And their lengths also may differ. Instead of 2 bits, it may be 3 bits, and so on. But the average code word length remains the same. This you can investigate by assigning a different way of 0 and 1s to the previous example, or placing the newly generated symbol in the second position. You can try that. I think I have an example after this. Okay, before going to that example or that investigation, let us see the third part of this question, that is how to find the variance. Because of this, that is as we discussed here, We can assign a 0 and 1 in a different way, or we can place the newly generated element maybe upper or lower in the sorted list. Because of these possibilities, we have choices, right? Because of this, we have a concept of variance that says here, the code, if you do like this in a different way, then the code words may be different. Their lengths also can be different. So we have a variation here compared to the average. That's the variance, right? A statistical word, variance. So that is represented as sigma square. The variance is always represented as sigma square. How much the value varies above the average value. That's the variance, statistically speaking. That's the general definition. So now that is equal to, for all symbols, probability multiplied by the difference between the number of bits in the code word minus average code word length. It's a square. So this is the structure of variance. If you see the general statistical definition of variance, we have that. Okay, here. So now we will use that here for this particular example. So what is PK? PK is the probability of the first symbol, that is 0.4. And what is LK? Number of bits, that is 2 bits, 0, 0, right? Minus, what is L prime? That we have found in the previous slide. Average code word length is 2.2, right? Okay, square. And the second symbol, probability is 0.2, and other things remains the same. So this is the code word length, this is L prime. Similarly here, for the last symbol, the probability is 0.1. It had 3 bits, 0, 1, 1 or something, minus 2.2, that's L prime, and it's square. The value becomes 0.16. Okay, that's the variance. Why do we have variance? That concept here, because we can represent the values in different ways. For example, 0 and 1 can be differently assigned. Similarly, the sorted elements can take the higher position or lower position. That's why we have variation in the average code word length with respect to the average code word length. So we will investigate that second case. What happens if we assign 0 or 1 in a different way, or we keep the newly generated element maybe at the bottom of the list instead of at the top of the list. We will see that. The same example, previous example. Now I'm going to investigate something else. I mean, placing it in a different order than what happens. And finally, we will conclude. So this is the first step of the Huffman coding. Please note, this is the same example, but I'm trying to solve it in a different way. Only a slight difference here. So first stage is sort the elements in the decreasing order. Second, consider 2 elements, lowest probability, and add them and generate a new symbol, that is 0.2. So in the previous method of solving, we placed this 0.2 newly generated at the top here. But now we will not do that. We will place it here, the sorted list. So your 0.4 is here, this 0.2 is here, this is here, and the newly generated one is at the bottom of the list. Again, it is in the sorted order. Next, you target these 2 elements, assign 0 and 1 to them, and what you generate is 0.4, right? Earlier we had placed it first, now we will place it not at the first, according to the sorted order. Okay, 0.4, it comes here. The first element is 0.4, it should be here. Next element is also 0.4, that comes from here. And this 0.2, that is here. From here it is. Okay, similarly, continue. Of course, now you get a 0.6 here. That should go to the first because that is the highest. And 0.4 is the lowest. And again, continue 0.1 and assign 0 and 1. Then you do the backtracking. From here, if you want to find out some value like S1, you do this. So S1 is what? S1 is 1 bit. I mean, the code word for S1 is 1, right? Backward path. So do that. So for S1, what's the value? 1. Similarly for S2, is it 0, 1? Yes, 2. S2 is where? Here. So what is the path? I should come here, 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 and here. Okay, so 0, 1 is S2. Okay, similarly, you can find S3, S4, and S5. Now, did you notice there is a difference between the code words previously generated and now? The same example. Earlier, there were 2 bits, right? Here, something like 0, 1 or something. And the last one had only 3 bits. Now we have 4 bits. Did you note the difference? Yes. So now we will find out the average code word length. How to find the average code word length? The probability multiplied by the number of bits in the code word. Right now we have only 1 bit here, right? So this is 0.2 multiplied by 2, 0.2 multiplied by 3. This is 0.1 multiplied by 4. Yes, 0.1 multiplied by 4. So average code word length is again 2.2. So whatever you do, either you place it in the first position or in the second position, or you may place the 0 below, 1 above. That's also possible. Then whatever the case, then the average code word length remains the same. That is what we concluded before. That now we are witnessing that. And we have also seen that the code words may change. Their lengths may also change. That is what happened here. Okay? Then now the variance. Variance is what? Variance is probability multiplied by length of the code word and this value, L prime. So for this case, the first symbol, 0.4 multiplied by 1 number of bits in its code word minus 2.2 here generated now, L prime. Similarly, you find out for all the symbols, the variance value is 1.36. So is there any change in the variance value? Maybe we have found the variance in the previous step. I'm just going back to see whether what was the variance value. Here it was 1.16. Now it is 0.36. I'm just trying to come back to the slide, what I was referring to, 1.36. The variance has increased, right? Much variation with respect to the average value. Okay, so this is the maybe last slide. Or I have one more slide, 1 more minute to spend. Okay, the takeaway from today's discussion, the main takeaway is should move the combined symbol upwards to get a minimum variance. Minimum variance is better because that says less variation with respect to the average value when you generate a code word. So it is better to use the first way of solving the problem. When we had generated a new symbol and you want to sort it, if there is another element having the same value, you move this new generated element to the first position. That is what we did in the first example, right? First way of solving the same example. So that is better because that gives a variance of 1.6. Now here we did a different method, right? We placed the new element in the bottom of the list. So it gave us a higher variance. Not so good. So best one is to move the combined symbol up topmost possible to get the minimum variance. This is why Huffman suggested to move the first generated element, I mean the newly generated element, to the top of the list. Of course, there were other possibilities like we have done here, but they don't give us the better performance. That's what. Okay, now some questions for you to think and solve. They are open-ended questions. Are we better? I mean, today's scheme. So we have 5 symbols, S1 to S5. Now we have assigned a Huffman code, right? S1 recently, I mean, the latest example, I represented S1 by 1, S2 by 0, 1, S3 by 0, 0, 0, S4 by 0, 0, 1, 0, S5 by 0, 0, 1, 1, right? Totally 14 bits. That is the second method I used. Similarly, you can write about first method. I just referred here the second method. Okay, if you use ASCII, then there are 5 symbols, each occupying 8 bits. We need 40 bits. So of course, this Huffman is better than ASCII because it's a variable length coding. But another question here, that's a boiling question I have written. A boiling question, which is better? The Shannon coding, the first method what we studied a few days before, or Shannon-Fano encoding scheme, which is studied later, and Huffman coding scheme, that is what we studied today. Which is better? Do you have any insight? So
Sir, I think it depends upon the statistical probability of each individual symbol occurring from a machine. Depending upon that, we have to choose such an algorithm which is more efficient.
in case the question is one, because Shannon coding, Shannon Fano, or Huffman, what's the input for all this? The same, right? Probabilities. I give you one question. I have three symbols, S1, S2, S3, and symbol probabilities maybe 0.3, 0.2, and zero 0.5. Suppose if you use Shannon coding, Shannon Fano coding, Huffman coding, which should be doing better? That's what the question is.
Huffman.
Why?
Because it's less time, it's not time consuming.
So you're talking about time complexity. So in case of
Yeah.
time complexity, Huffman is better, you're saying, right?
Yes, sir.
Any other parameters do you want to investigate? Maybe like the entropy or average code word length, efficiency? You have any comment, or someone has any comment? Okay, so this is the end of today's presentation.